Welcome to our deep dive. And today we're going to be tackling something called phenomenological velocity.
Ooh, that's a mouthful.
It is, and I'll be honest, I'm,
Yeah.
I'm still wrapping my head around it a bit,
Yep.
but from what I gather, it's a way of analyzing equations, especially in physics and cosmology, and these equations have parts that look like they should just cancel out,
Right.
but actually, they might have some hidden depths.
Yeah. Yeah, it's like those magic eye posters
Oh,
where
yeah.
you stare at it and there's nothing there, but then suddenly
It pops out at you.
a whole new image pops out.
Exactly. And
Mhm.
and to make things even more interesting, we have a really cool mix of sources for this deep dive.
Okay.
We've got academic papers, we've got excerpts from a book on the topic,
Mm-hmm.
and even some programming code. So,
Wow.
yeah, we're really going deep on this one.
I like it.
And one of the things that really caught my eye in the source material was this idea of math texture.
Math texture.
Yeah, so it's like
Mm.
architecture, but for math. So the idea is that equations have a kind of like underlying structure, a logic to them, almost like a blueprint.
Interesting.
And it's not just about the numbers themselves, but also the structure
Yeah.
and what it reveals about like deeper patterns and connections.
Okay. Starting to see where this is going.
And get this,
Yeah.
there are potential connections to the Big Bang and even some theological implications, which we'll talk about a little later.
Oh, wow. This could be good.
So are you ready to unpack phenomenological velocity?
Let's do it.
All right, let's start with the basics. Can we break down what phenomenological velocity actually is? For someone who isn't a physicist, what's the core concept here?
Sure. Imagine you're trying to calculate the height of a cone.
Okay.
But this isn't just any cone. It's formed by the difference between two circles.
Okay.
And you're using the Pythagorean theorem to do it. So you might think that all the terms relating to the height would just disappear from the equation.
Yeah, it seems intuitive that they'd cancel out.
Right. But that's where it gets interesting. They don't, and that's where phenomenological velocity comes in. It's about exploring what happens when we don't ignore those seemingly insignificant terms. What if they're hinting at something deeper? Like a hidden dimension or a connection we're missing.
Hidden dimensions. Okay, now you've got my attention. How does this tie into what we already know about physics,
Right.
especially things like Einstein's theory of relativity?
Well, the Lorentz coefficient is a key part of Einstein's theory.
Right.
And in simplified physics problems, it often cancels out neatly.
Mm-hmm.
But phenomenological velocity challenges that neatness. What if? Instead of letting it disappear,
Yeah.
we investigate what new insights emerge from keeping it in the equation.
So it's like we're intentionally keeping a piece of the puzzle that we usually discard just to see what happens.
Exactly.
I can see how that might lead to some unexpected discoveries. But you mentioned hidden dimensions. Can you unpack that a bit more?
Sure. One of the most fascinating aspects of phenomenological velocity is how this exploration might shed light on mysteries like dark matter.
Oh, wow.
We can't directly observe dark matter, but we know it must exist because of its gravitational effects.
It's like we know there's an elephant in the room because everything else is reacting to it,
Yeah,
even though we can't see the elephant itself.
that's a great analogy.
Thanks.
So what if phenomenological velocity, with its focus on these hidden parts of equations, provides a new way to understand and even quantify dark matter?
Okay, that's a pretty big way. What if, let's shift gears a bit and talk about this term I found in the source material map texture.
Uh-huh.
It's not every day you hear about equations having architecture. What's that all about?
Well, math texture is the idea that equations aren't just random strings of symbols.
Okay.
They have an underlying structure, a logic, almost like a blueprint with a deeper meaning.
Mm.
And the phenomenological velocity equation itself is a great example.
So it's like looking beyond the facade of the numbers and seeing the framework behind them.
Exactly.
How does that play out in the phenomenological velocity equation specifically?
Well, it uses a technique called bracketing, inspired by the philosopher Edmund Husserl. And it's about setting aside the parts that seem impossible or paradoxical. The parts we'd usually just cancel out.
Right.
And instead working with the parts that make sense.
Hold on, I need to make sure I'm following you. Are we saying that instead of trying to force the entire equation to make sense, we're focusing on the parts that we can understand and seeing where that takes us?
Precisely, think of it like working with a puzzle where some pieces are missing or don't fit.
Okay.
Instead of giving up, you find a way to work around the gaps and see if you can still solve it.
That's a really helpful way to visualize it.
Good.
So instead of getting bogged down in the parts that seem impossible, phenomenological velocity allows us to work with what we do know and potentially uncover hidden connections.
That's the beauty of it. by bracketing those impossible elements, we might reveal new solutions and connections that traditional approaches miss. It's about looking beyond the limitations of how we usually do things and embracing a deeper, more nuanced understanding of reality.
Okay, I'm starting to see how this could be a game changer, but before we go too far down that rabbit hole, you mentioned something earlier about the equation itself being like a new language.
Right.
Can you tell us more about that?
Just as we use language to express complex ideas, researchers are exploring phenomenological velocity as a mathematical language for describing the intricacies of cosmology and quantum mechanics.
So we're not just talking about crunching numbers, we're talking about a new way of expressing and understanding complex concepts.
Precisely, this language allows us to articulate ideas that were previously beyond our reach. One of the key elements is transforming the equations into language strings, which are condensed representations of the mathematical relationships. This gives researchers a more flexible and intuitive way to work with them.
So instead of wrestling with lengthy, complex equations, they're using these language strings as shorthand for the same ideas.
Exactly.
Sound like that could be a powerful tool. What are some of the things they're using this language to describe?
Well, for instance, they're using it to express the curvature of space-time, which is essential for understanding gravity and the universe's large-scale structure. They're also exploring the behavior of energy at the quantum level, where things get incredibly bizarre and counterintuitive.
Quantum mechanics is always a wild ride. Can you give us an example of how this language string approach is being used in that context?
Sure, one tool they're using is Fukaya categories.
Fukaya categories.
Yeah, it might sound intimidating, but it's a way of describing how different energy states interact, like musical rules governing how notes combine to create harmonies and melodies.
Okay, I can grasp that. So instead of looking at energy states in isolation, Fukaya categories help us understand how they relate to each other and create the complex symphony of the quantum world.
Exactly. By using phenomenological velocity as a language, researchers hope to decode the intricate music of the quantum world, potentially revealing new insights into the fundamental nature of reality.
This is all starting to sound incredibly profound. I'm
Yeah.
curious, is phenomenological velocity just a theoretical concept, or can it be practically applied and visualized? I noticed that you included some code examples in the source material, which suggests it's more than just an abstract idea.
That's a great observation. Phenomenological velocity isn't just confined to textbooks. It can be brought to life through computer simulations and visualizations. The code examples you mentioned are a testament to that.
So are they creating simulations of the universe using this concept? Like a cosmic video game where you can tweak the laws of physics and see what happens?
You're on the right track. They're building virtual laboratories to test their understanding. One technique they're using is called the M-posit transform, a way of warping the topological manifold of the equations. It's like being able to manipulate the very fabric of the mathematical landscape.
Well, on warping the topological manifold. That sounds incredibly sci-fi. Can you break that down for us non-physicists?
Imagine a video game where you can adjust gravity or the speed of light. The M-posit transform allows researchers to do something similar with the equations of phenomenological velocity. They can change the parameters, tweak the variables, and essentially play with the equations to see how they behave under different conditions.
So it's like they're running experiments on the universe within a digital realm.
Exactly, and these simulations allow them to gain deeper insights into phenomenological velocity itself, while also uncovering potential connections to other areas of physics, like string theory and quantum gravity.
This is all so mind-expanding, and the fact that we can now visualize these complex concepts, even if we don't fully grasp the math, is truly remarkable.
I agree, the visualizations in the source material are stunning and bring the concept to life in a way that words simply can't.
I'm definitely going to be checking those out. Speaking of seeing it's time to tackle one of the most intriguing aspects of this whole concept, the connection to the Big Bang and those theological implications.
Yes, that's where we delve into the truly profound implications of phenomenological velocity, where the mathematical meets the metaphysical.
Okay, you've officially piqued my curiosity. Let's dive in. One of the things that really jumped out at me from the sources was this idea of finding existence from non-existence in the context of phenomenological velocity. It's a pretty weighty statement.
It speaks to the very heart of creation, the emergence of something from nothing, and it's directly tied to the behavior of the Lorentz coefficient within the phenomenological velocity equation. Remember how we talked about it seeming to disappear only to reappear in a new form?
Yeah, it's like it's playing a cosmic game of hide and seek.
Precisely, that process of vanishing and reappearing is seen by some as a mathematical metaphor for creation itself. The Lorentz coefficient, which relates to the speed of light, could be interpreted as representing a type of non-existence when it cancels out. But then through solving for phenomenological velocity, it emerges, again, transformed and imbued with new meaning.
So like the universe itself arising from a state of nothingness and transforming into the complex reality we observe today.
That's one way to interpret it. And this resonates with some of the deepest questions in theology and philosophy: the origin of the universe, the nature of creation, the possibility of something arising from nothing.
It's almost as if phenomenological velocity provides a mathematical framework for these age-old philosophical and theological inquiries, suggesting a link between the laws of physics and the mysteries of existence itself.
Precisely. And it's important to remember that we're not trying to prove or disprove any particular theological viewpoint here.
Right.
We're exploring the potential for a deeper understanding of the connections between science, mathematics, and the profound questions about the nature of reality.
It's a reminder that even in advanced physics and cosmology, we're still grappling with some of the same fundamental questions that have puzzled humanity for centuries, but now we can approach them through the lens of concepts like phenomenological velocity, which is both exciting and humbling. Are you ready to move on to part two?
Absolutely. There's much more to explore.
All right, let's take a quick break and we'll be right back.
Welcome back to our deep dive into phenomenological velocity.
That idea of finding existence from non-existence has really stuck with me.
It's powerful, isn't it?
It is, and it highlights how this concept could connect science and philosophy. But for now, let's move to something more concrete. You mentioned using phenomenological velocity to create language strings.
Mhm.
What are those, and why are they important?
Remember earlier we talked about phenomenological velocity being like a new language for describing complex concepts?
Yeah.
Well, these language strings are like the words or phrases within that language. They're like condensed versions of the math in the equations.
So instead of using long, complicated equations, researchers can use these language strings to explore these concepts more efficiently.
Exactly. It's like using shorthand for complex ideas. And these language strings are really versatile. They can describe lots of things, from the curvature of space-time to how energy behaves at the quantum level.
We touched on Fukaya categories earlier, and they seem important for this language string approach, especially when talking about quantum mechanics. Can you remind us what those are and how they relate to a curved energy landscape?
Of course, Fukaya categories are mathematical tools that describe how different energy states interact. They help us understand how these states relate and combine to create the complexity of the quantum world. The curved energy landscape is a way to visualize these interactions. Imagine a mountainous terrain where each peak is a different energy state, and the valleys and slopes show the transitions and pathways between them.
Okay, I'm starting to see it. So the shape of this landscape, its curves, represent the rules that govern how energy behaves at the quantum level.
Exactly what's fascinating is that phenomenological velocity through these language strings might give us a way to map and navigate this complex energy landscape and potentially unlock how energy flows at the most fundamental level.
You mentioned hidden dimensions earlier, something that's always been hard for me to grasp. Can we go a little deeper into that?
It challenges how we think. We're used to a world with 3 spatial dimensions and 1 time dimension. But what if there are more dimensions that we can't directly see? What if they're hidden from our everyday experience?
That's a lot to process. Do you have an analogy that might help?
Imagine a garden hose stretched out from far away. It looks like a one-dimensional line, but if you look closer, you see it has a second dimension, the circumference of the hose. Now imagine that second dimension is so tiny that you can't see it. It's still there, but hidden.
So are you saying there could be other dimensions curled up too small to detect, but still affecting the universe at a fundamental level?
Exactly. And phenomenological velocity might be sensitive to these hidden dimensions. The behavior of the equations, the interaction of the language strings could give us subtle clues about these hidden dimensions.
That's incredible. But if they're hidden, how can we study them? It seems impossible.
It's tough, but not impossible. Remember those computer simulations we talked about? Those could be key to exploring these hidden dimensions. By changing the equations, by adjusting the language strings, researchers might be able to create models and visualizations that show us the hidden structure of the universe.
So we're using math to reveal parts of reality that we can't directly perceive.
That's a great way to put it. That's the exciting part of phenomenological velocity. It's not just about solving equations, it's about understanding the universe and reality itself.
I'm starting to feel a sense of awe. It's like we're close to a whole new way of understanding the cosmos.
I feel it too, and remember, we're just getting started. There's still so much more to discover.
For sure, in the last part, we still need to talk about those code examples and how those simulations are being used. And we have to unpack that term Composite transform.
Right. The composite transform lets researchers warp the topological manifolds of the equations. Essentially, they can experiment with the very fabric of the mathematical landscape.
Sounds like we're in for a wild ride in part 3. Welcome back to our final part. We've covered so much about phenomenological velocity, from the basics to the philosophy, and now let's see how researchers are using technology to explore this.
Yeah, it's time to get practical.
Right. Those code examples you gave really caught my eye. It seems like we're going from theory to actual hands-on exploration.
Absolutely, technology has given us new tools to see the universe.
So what are researchers doing with these simulations? Are they like creating digital models of the universe and then changing the parameters to see how phenomenological velocity works?
That's a good way to think about it. They're building these virtual labs where they can test and refine their understanding of the concept. And a big focus is the relationship between phenomenological velocity and the curvature of space-time.
Can you explain that a bit more?
Sure, they're creating simulations where they can change the curvature, add different types of energy and matter, and then see how phenomenological velocity acts in those scenarios.
So it's like a virtual sandbox where they can play around with the fabric of the universe.
Exactly, and by doing that, they hope to learn more about how gravity works at its most basic level. Remember, gravity is the curvature of space-time, and phenomenological velocity might be the key to understanding it.
Speaking of unlocking secrets, you mentioned the composite transform earlier, which
Yeah.
sounded pretty complex. Can you explain what it is and how it's used in these simulations?
The composite transform is a way to warp and manipulate the topological manifolds of the equations. Think of it like a set of tools to stretch, bend, and fold the very fabric of space-time in the simulation.
Okay, I think I'm getting it. It sounds incredibly powerful.
It is one really interesting application is in studying black holes, those areas of space-time where gravity is so strong that nothing, not even light, can escape.
So how does the composite transform help us understand black holes?
Well, it lets researchers create simulations of these extreme environments and study how phenomenological velocity behaves near the event horizon, the point of no return. They're basically making a virtual black hole and watching how phenomenological velocity acts inside it.
It's like doing experiments at the very edge of reality.
Exactly, and they're finding that phenomenological velocity might act in unexpected ways near a black hole. It could even change how we think about space and time in those extreme environments.
That's amazing. And the fact that we can actually see these simulations with computer graphics is incredible. It's like watching the universe dance.
I agree, the visuals are stunning. You can see the curvature of space-time, the warping from the composite transform, and the flow of phenomenological velocity, all in amazing detail.
So as we wrap up this deep dive into phenomenological velocity, what are the key takeaways? What does it all mean?
That's the big question, isn't it? We're still in the early stages of understanding this concept, but here are a few things that stand out. First, phenomenological velocity is challenging what we thought we knew about the universe. It's making us rethink space-time gravity, even reality itself.
Like it's a new lens to view the cosmos.
Yeah. Exactly. Second, phenomenological velocity is giving us a new language, a new set of tools to describe and explore the universe. These language strings, the Fukaya categories, the composite transform, they're all part of a growing toolkit to delve into the universe's mysteries in ways we never thought possible.
It sounds like we're just scratching the surface of what phenomenological velocity can show us.
We are. And lastly, this exploration reminds us that our journey of discovery is far from over. There's so much we don't know, so much more to learn, and that's what makes science so exciting.
It reminds us to keep asking questions, keep exploring, and keep searching for a deeper understanding of the universe and our place in it. Thank you so much for guiding us through this fascinating deep dive.
It was my pleasure.
And to you, our listeners, thanks for joining us. We hope you found this exploration of phenomenological velocity insightful and thought-provoking. Keep those brains working and never stop exploring.